All right, I'm going to be talking about ESPC, energy savings performance contracting for the industrial market of the federal government. And we see most of those types of projects in the military bases. I was talking to somebody yesterday about this, and they were surprised that we do the kind of things we do on these military bases. They don't realize that the Air Force, the Army, and the Navy take their planes, their ships, their Humvees, they take them apart and they recondition them from scratch. And so, you'll have plating shops, you'll have painting facilities, blasting facilities, compressed air, big painting hangars to paint the big hangars. So that's the kind of work we do. But this person was surprised that the military does that and that they don't outsource it. They do it themselves. Okay, I'm going to go over energy savings performance contracting, and I'm going to talk a little bit about how you get these things to pay back, the types of ECMs that we implement for these process ECMs. And one of the things that happened when we first started doing ESPC about 15 years ago with the government, that they stayed away from these industrial buildings and from these processes. They didn't want you to touch them. Do the lighting, do the controls, do the HVAC, but don't touch my process. Today, they realize that on an industrial base, 60 to 70% of the energy is consumed by those processes that you're not touching. So today, they are touching them. And we're doing several bases right now where we're doing ESPC on industrial systems. Okay, right here, just what performance contracting is for anybody that doesn't know, is you take the baseline energy and O&M, operations and maintenance costs for a facility or a base, and you are doing energy conservation measures that reduce those costs. Save energy, save O&M, and those funds here in 2 will fund the project. And with the federal government, you can amortize 25-year term. So that's a payback today. In today's world, it's a payback of about 12 years. That's a pretty good payback. You can do a lot with that, especially if you're able to capture O&M savings. If you're trying to do big mechanical projects with just energy savings in the United States, it's really hard to cash flow at a decent payback. So make sure you go through the effort of seeing what kind of operations and maintenance it will save too, okay? All right, I wanted to show you what the energy profile looks like, and this is in the CD that you guys probably have, this presentation, but to show you what an industrial building looks like, as far as the cooling and lighting and what you typically see for just a simple office building, large office building. And it's about 58,000 BTUs per square foot of electric consumption. And gas, when you add in the 17.4, it's about 75,000 BTUs per square foot electric and natural gas for a typical commercial building in the mid-United States, the middle of the United States. Now, if you look at industrial, this is real data from a lot of industrial facilities, and this is fabricated metal products. It's pretty similar to what we're probably doing on these military bases. That number is 285. So if you look at it, comparing the two, an industrial plant is going to be 4 times higher energy consumption than a typical commercial building. Hello, guy. Okay, this is an actual performance. The federal government's required to save energy based on the executive orders, and an industrial base. This is an Air Force base we've been working on for about 8 years, and we started out at 234,000 on this particular base. And like I showed before, 285 we consider, in that range, it would be an industrial base, industrial facility. And then down here is where we're projected to go. Right now, we're right here. We've already 37% reduction, and we've got a really big project coming up, which is going to be looking at the industrial processes, and that'll get us down to 102, or 56% reduction in energy. So there's a lot of potential for energy savings if you include the industrial, and you also include operations and maintenance savings. Okay, what did we do to reduce the EUI? That's what I'm going to kind of cover here, to show you some of the industrial projects that we did, ECMs, so you can see where we saved the energy. This is kind of a listing of some of the industrial, and we do those in addition to the typical lighting, water, EMCS, energy management control systems, and building envelope ECMs, the simple ones, okay? And some of the really, well, these are all really big energy consumption, you know, like compressed air, corrosion control facility. What that means is painting facility, big painting hangars that sandblast and paint big planes. Okay, they take them apart and they do all of that work. A lot of energy consumption. I'm going to show you that in a minute. Foundry, heat treating. They do their own heat treating. This is a really big one. Stripping, dipping, cleaning, and painting. These dipping tanks, cleaning tanks, plating tanks, these industrial bases will have like 150 of these tanks. And they're filled with water or some kind of chemical, or they do plating, and they're open top, and they ventilate. And if you go in and you modernize those plating facilities and cleaning tanks, and you put in automated tops, you could save a lot of energy. I'm going to show you that here in a minute, on the kind of energy you could save when you're doing that. What we look at is we get rid of steam, if we can. Big central steam plants that they have. They're very inefficient, okay? And so we try to go to a distributed heat where we'll have a building out here that needs some kind of heating, and we try to put in a condensing boiler. This is a condensing hot water boiler to provide, you know, the heating hot water more efficiently. It can also supply the hot water to the processes. But it's got everything mounted on here, and you know, you're getting efficiencies of from 90 to 98%, and that's compared to central steam plants, 50% if you're lucky. When you add it all up and look at the seasonal efficiency, you're just wasting a lot of energy. Here's the performance curves. This happens to be the boilers we're using right now, and these are other manufacturers, so they're not all created equal. You got to really look at their performance data. And on a condensing heating equipment that does condensing, it's always based on some parameter. Like on a boiler, it's the incoming water or the return temperature. That's how that you improve that efficiency. The further you can get that return temperature down, and the older systems are usually a supply temperature of 180 and a return of 160. You want to make sure you design these systems, if you can, and change them to where you have a bigger temperature difference. And have a lower temperature. Don't do 160 return. Try to get down to 120. Get a much higher efficiency out of those boilers. So it's very important how you control those. Be very careful, because if you can't, a lot of times you'll have these heating coils out there. They may only be a 2-row or 3-row coil, and they need to be a 6-row coil to be able to work with that kind of a split temperature. So you might have to do some renovation out there to get that to fully work. But eventually you're going to replace that coil or that air handler, and make sure you put in a hot water coil that has more rows, so you can operate at a 120 to 160, you know, higher split. Steam boiler, this is an actual project I did, but it's just a small steam boiler. These steam boilers we work with, like Tinker Air Force Base, they're huge. They're as big as this part of the conference center. You know, they're huge. Well, this is just a steam boiler, and it just kind of shows you how they operate. They're just so inefficient. You know, they're just fire, and they're just making steam, and they're heating everything up, and you're lucky if you get, 40 to 50% efficiency out of them. Get rid of them. Today, this is an actual installation. See how small the condensing boilers are? They're replacing these big fire tube boilers. I mean, they take up a lot less space. It's the way to go. Gas infrared. So if you're getting rid of steam and you have like a warehouse or a shop or some kind of a high bay area like a hangar, use gas-fired infrared heating. It's much more efficient on high bay buildings. It's the way to go, I'll tell you that. And by the way, this Ambirad, that particular manufacturer's at the show. He's got an exhibit booth there, and so does Guy on thermal storage, if you're interested in that. Put a plug in for you there. Yeah. Okay. Oh, direct gas fired. So you're going to have a lot of makeup air in these industrial facilities, and they've probably got steam coils. And those steam coils probably freeze every other year, and they're changing them out every other year. Get rid of the steam and go with direct gas fired. This happens to be a Maxon burner, which is a Honeywell product. We don't have to use that, but happens to be Honeywell. And so if you're converting makeup air from steam or hot water to natural gas, direct gas fired. And some people think because you're burning the gas and dumping everything in the building that that's a problem. It's not a problem. Okay, only in buildings like sleeping quarters you wouldn't do that, because these buildings are going to have ventilation, enough ventilation to handle the CO2 that is in the burned gas. So it's very common to do direct gas fired in a building, open bay types buildings. Also, it's not 100% efficient. People think because you dump it all into the building, all the energy is in the building. Well, about 10% of the gas is used to make water, the hydrocarbon. You get the hydrogen in the fuel, and the oxygen in the air makes water vapor. So you lose about 10% of your energy just making water vapor. If you're using it in makeup air, it doesn't ever condense. Like in a condensing boiler that you can lower the temperature of that flue gas and get that energy back. This doesn't, because the air is really dry. It just sucks up that moisture, so it never condenses back. You never get that energy back. But if it's a facility like a painting facility where they need the humidity, it's a benefit to have that. So you'll get a certain amount of humidification out of a direct gas fired on a painting facility. Corrosion control hangers, they're really big energy consumers. They do these planes that are, they're as big as a 777, huge planes they do in these military bases. And they're always 100% outside air because they're older designs. You only need to be 20%. As far the commercial industry allows 20%. And the Air Force and Army has done some hangars at 20%, so that's a big energy saving opportunity. Because this particular one, 500,000 CFM of outside air was about $2 million a year to heat and cool that hangar. And they had to heat and cool, because painting, you need cooling. If you're just stripping, all you need to do is heating. But for painting, they heat and cool 24 hours a day, 365 days a year. So there's a big opportunity for savings on these corrosion control. You have to have humidification for when they're painting, yes. They got to maintain about 40% relative humidity. So that's another problem, because they never last. These steam humidification systems don't last. So we prefer going to other types of systems that are not just steam injected into the ductwork. Go with like a Nortex system that's a gas-fired. Excuse me? We do if we do some kind of, heat recovery and stuff. Yeah, sure. And this is a model. We do EQuest models because we want to model. This is ESPC. This is Energy Savings Performance Contracting. The ESCO is responsible for the energy savings. We've got to make sure we calculate the savings properly. So we use a model, 3D model. This particular corrosion control hanger, painting hanger, almost $1 million a year in savings in just one building. It's a big number. And that will fund $10 million worth of work. If you take the payback, about 12 years, 12 times that, it's about $10 million it funds on energy savings. So the ESCO will come in, do all the work, guarantee the savings, and you don't have, out of your budget, you don't spend anything. That $10 million just comes out of the project. So it's a good deal. CFDs, computational fluid dynamics are required on these plane hangars because they have to have, velocities of like 100 feet per minute, between 80 and 100 feet per minute for the paint to cure properly. So that's why they have so much air, makeup air, is this wall of air is moving across that plane to make sure that that air is maintaining around 80 to 100 feet per minute, or it doesn't cure properly. Plating shops. These are finishing shops. Really big energy consumer. And when we see these, you go, oh, God, what do I do with this? These tanks and pipes going everywhere. And once you figure them out, they're not so bad. And so we're renovating a couple of these, and they're huge projects for the Army and the Air Force. And what we do is, we're benefiting on all these different systems. Blowers, air compressors, boilers, chillers, scrubbers, industrial waste. Ventilation is a real big one. These are the kind of ECMs we do. The really big ones are like, ventilation. Because if we go and automate one of these tanks and put an automated closure to close automatically when it's not being used, the CFM to ventilate that tank is cut to 1/10 of what it is when it's open. So if you're 1,000 CFM, it would be 100 CFM when you're closed. So you really save ventilation energy when you do things like that. VFDs, we put VFDs on the makeup air units and the exhaust fans. We convert the steam, usually to natural gas firing. And I'm going to show you in a minute why, because steam costs a lot. Besides being very wasteful, it costs a lot of money. I'll show you that in a minute. I'm almost done. What time, how am I doing? I'm doing fine? Okay. If I finish early, I'll just give you more time. Okay? This is a real job I'm doing right now, and these industrial buildings, they'll have these open tanks. They're uninsulated, boiling water. They're using steam to heat it, and they're just on all the time. So what we'll do is we'll go in and insulate the tank. We'll try to change from steam to hot water. You can't always get rid of all your steam. Where you do have steam, you do it very efficiently, okay? But we'll put these automatic closures on the tanks. So when they're not using the tank, close it. At night, when you're not there, turn it off. So we'll put in controls to do that, okay? There's two different tanks here. Here's the different kind of heat exchangers they use. A lot of times they'll do steam. I'll try to do hot water. This is an internal heat exchanger. This is an external brazed plate heat exchanger. And this is an electric. Depending on what you want to heat with, you can do anything you want here. You can change it. Ventilation, there's a lot of ductwork coming from these tanks. And they make big old makeup air units and scrubbers, scrub the air, for the environmental, the exhaust fans. A lot of energy being consumed. This is an example of where this is a new design for a new system, not by us. We would have done it differently. Where they're leaving some of the tanks open. Don't open the tank. Put closures on them so you can reduce that ventilation. So they're having to do, like right here, 2,400 CFM. If they close that top, if they put a top on it, it would only need to be 240 CFM when it's closed. And most of the time, they don't use them. They'll have 150 tanks and they're using one tank. So why not close all the other tanks that you're not using? These have closures, but they're only reducing their consumption in half, on some of these. Or a third. Well, you can go down to 1/10. You don't have to go just to 1/3. You don't have to be that conservative. So there's a lot of places to save energy. Also, these tanks are pull. They're pulling on each side for ventilation. If you did push-pull, where you push the air across the top and pull, you cut the energy in half. The ventilation air is cut in half. Okay? You don't have to have as much air because you're not pulling from both sides. You're pulling from one side, and you only have to do half. It's a more efficient way of ventilating an open tank. Here's just another diagram of this project. Here's real life tanks. It's like here's the ventilation pulling from one side. Here's your ventilation ductwork. Here's a 3D rendition of what we're doing at Rock Island, where you see these tanks, new tanks, and they've got these automated tops here. Okay, look at all these tanks here. Just hundreds. And then, like here, you can see the top where they open, close. Okay. Here's another set of tanks. And also the metallurgy is very important. One of our contractors put in PVC on one tank, but the temperature was too high and the ductwork melted. So you got to make sure you're applying the metallurgy right. If you're going to use PVC, make sure it's not high temperature on a high temperature process. So stainless or PVC is better. Here's just another one. See all the automated tops here and the automated hoist system that automatically moves the parts. Here's just a calculation. I won't go over it, but this is Rock Island. Just the makeup air is steam savings over $2 million a year. Okay, that's worth about $25 million worth of work on performance contracting. And right here, electric, almost $500,000. Now, steam. Here in D.C., steam, I don't know how many buildings you have on the central steam system here. You have your own plant. You have your own plant, that's right. But these other ones, like we took HUD headquarters off of the central steam that the GSA owns here. And GSA charges over $40 a million BTU. If you compare that to regular natural gas, in the Midwest, I'm paying $4. It's almost 10 times more expensive to use that steam. It's because of O&M costs, operations maintenance costs. And the steam here at this military base is about $20. So it's still expensive. Okay? How am I doing on time? 5 minutes. Okay, thermal spray booths. These are pretty complex, and they spray kind of a molten ceramic or some kind of a high wear surface onto these metal parts. They have to be cooled. So they have these air-cooled chillers, which are very inefficient. You know, tie it into your central chill water system that's more efficient. You know, that's one way of saving energy. Then also, you're going to have filters. They filter that air. And so these filters, you want to put VFDs on the exhaust fans and lower that airflow when they're not doing the thermal spray. They got to keep the room pressurized, but reduce the airflow when you're not doing the thermal spray with VFDs and the controls. Big painting booths. You'll see these painting booths. This is Rock Island, where they're just open to the space. So that whole big building there, you see the lights up there. This whole big building has this high ventilation rate. So it's better to go to more portable units like this. So if you put in a more portable unit, all you have to ventilate is that box, and you don't have to ventilate that whole building at a real high ventilation rate. Right here, it's showing you, typically, this is a direct gas-fired airflow diagram for a painting booth that you would buy from a commercial painting supplier, okay? And you get very high efficiency with the direct gas-fired, okay, 90%. You reduce the airflow tremendously. These also are recirculating 80% of the air. So instead of heating and cooling 100% of this airflow, you're only doing 20% when you're not painting. Some of the people that do this painting don't want you to do recirc when they're painting. But you could do it when they're not painting, when they're curing or when the thing's just sitting there. Compressed air. In fact, there's a session going on in parallel with this on compressed air. It's really big energy savings. We do a lot of compressed air projects. These compressed air, they're just so simple, they're so archaic that they just waste a lot of energy. they just cycle the air, 125 to 100 and back and forth, and dump any air they don't use in the system, because it's a centrifugal air compressor and you can't back off the airflow on a centrifugal. So it dumps all the air in the alley that you're not using. Very wasteful. So what we do is we automate it a little bit more. We put in a more efficient compressor that can load and unload. I don't have time to go over all of that. But we also put in this expander station. And this expander station is kind of the brains, where you separate the system from the compressors. So you operate your compressors the most efficiently as you can. You have more storage usually, because you probably need more storage for it not to dump that air in the alleyway. Okay? And then you maintain constant pressure going out to the people using the air. So it's whatever air pressure you need. It's not going to cycle between 100 and 125. It's whatever you need to be out there. It could be 60 psi. So you operate much more efficiently with that expander station separating the two. That's it. And there's my email. If anybody wants to email me and ask any questions, or me to help you, with one of your ECMs, I'd be glad to help. Okay? I'm done.